Good evening. Is the microphone on? Yes. Okay. Thank you. Good evening. Thank you so much for coming out on this night when we hope that the snow won't start until maybe 11 o'clock or something like that. But you'll be able to see whether it does, I guess, out the windows, beautiful picture windows. My name's Sister Kathy Duffy, and I'm the director of the Institute for Religion and Science at Chestnut Hill College. And as the director, I would like to welcome you here to SugarLoaf, our SugarLoaf campus, and to this evening's lecture. As many of you know, the Institute is attempting to promote the constructive engagement of religion and spirituality with science and technology. To encourage dialogue that's interfaith, multi-science, and civil, we sponsor lectures, a reading circle, and a variety of other events, as well as provide a growing number of resources. One of the latest things is we've added a couple videos of past lectures, so do look at our website, for those. And also you can, look for other resources. We have books in our library that are dedicated to this topic, and also every once in a while one of our advisory committee members writes a blog, so keep your eye on our website. Also, if you have never come here before and you didn't get an email, do sign up at the back on the mailing list. We send out mailings, a couple weeks before events. So it's good if you would sign up, and we'll keep you informed. Tonight we're very fortunate to have as our speaker Dr. Elliot Tommaro. Dr. Tammaro has a doctorate in physics from Bryn Mawr College, and although he is taught at both Bryn Mawr College and Villanova University, we're happy to say that he is now an assistant professor of physics here at Chestnut Hill College. One, by the way, who's very loved by his students, many of whom are here, right? Elliot's research has focused on the fascinating physics topic that is hoped to give us the longed-for theory of everything, string theory. But his research interests in theoretical physics are broader than this and focus not only on string theory and physics beyond the standard model, but also on quantum information theory and the foundations of quantum theory. Some of his work has been published in the journal Foundations of Physics. Tonight, Elliot will present the argument regarding free will from the side of the physicist who deals with atoms, nucleons, quarks, and strings. I'm sure this lecture will stir up some very interesting discussion. So let's welcome Dr. Tammaro.
Hi everyone. Thanks for coming. So I hope everyone appreciates my title image. When I decided on dominoes, I immediately wanted to change my title to Am I a Domino? Quite literally, because dominoes they're similar to us, frankly. They're different. You can identify one from another, and yet they do fall when they're pushed in a line. We wonder whether we're not more like them than what we'd like to think. So at the present time, a great debate is raging in physics circles, in philosophy, in psychology, in theology, and really quite beyond. The debate concerns nothing less than the existence of our free will, our precious free will. A naive argument for the existence of free will may invoke personal sensation. I feel free, damn it. I feel free. But feelings cannot be trusted. One might feel cold when they're hot with fever, right? We've all felt this. Sensation is also not a rational argument. I can convince no one in writing that I have free will because I felt it. The debate over free will is an ancient one. It's gone on long before and everyone here knows it will go on long after this talk as well. At the very least, it stretches back to the ancient Greeks. It's very likely that it started long before then. It's been argued in an uncountable number of incarnations from numerous backgrounds, including, but not all limited to, the philosophical, obviously, the political, certainly the theological, and tonight, and of special importance to us, the scientific. The topic is so very rich, it really cannot be done justice in a lecture series, let alone a lecture. I'm glad everyone took a look at this quote by Nobel laureate writer Isaac Singer. Of course, I believe in free will. I have no choice. It's certainly intended for amusement, but I think it does a fair job of highlighting the crux of the free will debate. In one sentence, if I were to summarize, it would be this. So, the topic of free will really can't be done justice by me. I wish it could, but it really can't be. It's too rich. It's too old. It takes many different standpoints. It takes the opinions of many people. But my goal for this evening's lecture is finite and achievable. I hope at least. Namely, I really want to open you to the debate. At least some of its history. I want to present you with the cruces of the free will problem. We're going to discuss the subtle implications and the common misconceptions, of which there are many. I really ultimately hope to inspire you to join this debate, which is, to me, both personally and hopefully to many of you here, of really great importance. Frankly, it's something that's near and dear to us, and we should get to the bottom of it. We should either defend if we think it's real, or we should cut down if we think it's artificial. But I think it's really important for us to be equipped with the tools. We have to be equipped with the tools to tackle this. Discussions of the free will problem, they may very well be opened from many different disciplines. There's exciting strides as we speak being made in neurobiology, in psychology, and elsewhere. But it's the sharpness and the mathematical rigor of the physical sciences which make it an especially appealing starting point and backdrop for our present discussion. It's for this reason that we will consider the free will problem as regarded to insights from physics. That is, we really want to frame it as sharply as it can be framed. I think that it's very often loose, too loose for my taste. So as not to mislead anyone, I really would like to emphasize that I cannot present at all a resolution of sorts to the free will problem. I believe ultimately that if there is a resolution, it can only come from within. It's something that we have to ask and answer on our own personal turf. I can, however, arm you with the facts. I can arm you with the previous debate. I can tell you what's coming. And then ultimately I can let you loose on the world. So let me first tell you a little about my own personal motivations for this lecture. So I'm a practicing, and I mean that, practicing Roman Catholic. Free will, moral responsibility, sin, among other notions, are part of my daily lexicon. I literally live by them, and will eventually die by them. Obviously, however, such unskeptical acceptance of these notions on my part is not easily found in the rest of the physics community. I'm sure you're all at least slightly familiar. I feel I have, accordingly, a bit of a burden to support my stance. With regards to research, a primary interest of mine, at least as of late, has been foundational issues in quantum mechanics. Fortunately or not, sometimes I think mostly not, It's in this area of physics in particular that discussions of the free will problem are becoming especially prominent. And all too often, free will is written off as an outdated mode of thinking. No matter what your personal view, I hope you leave this evening more sensitive to the other camp, assuming that we all fall into pretty well-defined camps. More generally, why should we care whether or not we have free will? I thought long and hard about this, at least in part in trying to write this talk, and the best reason that I could come up with, quite arguably, is that free will is an essential tenet of religions, of moral systems, and our laws. If for only this, it seems to be a valuable thing to consider. Free will and free action form the backbone of our society. Put bluntly, when our actions lead to positive results, are we deserving of the praise? Or when our actions lead to detriment, whatever that might be, something as harsh as crime or something as mild as offending people in the room, is that detriment left on our shoulders, or is it really not? Let's begin by attempting to define free will. A common and apparently satisfactory definition might be that the power of acting without constraint of necessity or fate, the ability to act at one's own discretion. It seems like a perfectly fine definition, but it's naive. Let's at least consider some of its difficulties. This definition seems to quite well apply to the actions of many living things. Imagine a child who's offered a set of treats, perhaps different types of candy. The child considers and decides on one, as per the rules of the game. I know most children will try to steal two. Supposedly, the child decides on the treat that she or he finds most delicious. Now consider a dog in a similar situation. The dog also decides on one treat, presumably the treat that it finds most delicious. It seems that both human and animal can act according to their own discretion, that both human and animal have a will on which they're capable of acting. Perhaps it's easy for some of us, are there animal lovers in the room? Perhaps it's easy for some of us to say that dogs, much like our children, have a kind of free will. Do you think this way, however? I ask the following. If dogs, then birds. If birds, then reptiles. If reptiles, then insects. If insects, then so on. Is there a divide? Or do all living things possess a kind of free will? To those among us who are religious, this might be especially bothersome. Because free will should be something unique to humankind. It should be a component that's integrally related to our soul, if I dare use the term. One might further question the meaning of the term free. Naturally, one might say that free refers to the fact that the decision of the will is made without influence from anything that is external. However, in our example, our opinions of the offered treats are in fact external influences. Perhaps we've heard a good thing about some treat and a bad thing about another. Likewise, whenever we make a decision of any kind, we may be influenced by an uncountable number of things. The comments of our families and friends, our own past experience, our hopes, to name just a few. You might protest immediately by saying that these influences merely enter our mind as extra information, similar to knowing which treat has the most sugar, for example. But do they tug at our will? Fundamentally, do they tug at our will? And I think that most of you would answer yes, that they function as a way to pull the will one way or another, And therefore, is the will free? Is it truly free? How should we define free will? Is there a definition that is applicable to humankind alone, i.e. that excludes animals? Is there a definition that allows us to sharply determine when one's will is free, when it's bound, when it's been tugged at? These questions are of great importance, and they do not have a clear-cut answer. I think most would agree that a simple literature search would demonstrate that there's a near infinite number of debates about this question alone. We're going to refer to this tonight as the lesser free will problem. Some have claimed that we should simply restrict our use of the term free will to questions of morality. They suggest that we wield our free will only when we choose between right and wrong. Now, whether this is a reasonable turn to make, I'm not going to answer. But it is at least not a useful definition for our present purposes, because we're attempting to enter into a debate where moral or theological statements do not immediately have any weight. In this lecture, we aim to consider only statements that have weight under scientific scrutiny. That is, we wish to make statements that are empirically falsifiable so that we can make them with people who want statements that are empirically falsifiable. If you debate this amongst religious folks, by all means, take this turn. But for us here now, it's not a reasonable thing to do. Philosophers and theologians often modify the naive definition of free will with a statement concerning a human's ability to act differently even if all other things were equal, a feature referred to as indeterminism. We'll return to this shortly. This is an important point, that people might be special. It is at least possible that despite the similarity in appearance between the acts of will of animals and humankind, they are different. If all things were equal, any non-human living thing might act exactly the same way. That's a possibility. While a human may in fact be able to act differently. Also a possibility. Once again, we should ask if this statement has weight under scientific scrutiny. Can we falsify any of these claims about differences between animals and people? Many experiments have been conducted in an attempt to more deeply understand the action of the will in animals and people alike. Consider a recent result. An experiment performed by Bjorn Brehm at the Free University of Berlin. It goes something like this. Fruit flies were attached to a torque meter, so that as they attempted to fly, the direction and the magnitude of their wing beats were recorded. Note, they're attached. They're not actually flying anywhere, but they tug on a little device which makes an electric record of their would-be flight path. They're placed in a completely uniform container. It was white in the experiment, so that they have no outside stimulation, visual or otherwise. There's no image. They're completely surrounded. There's no breeze. There's nothing to influence them. They literally have their own little fruit fly mind and the decision to make up as to where they're going to fly. The flight trajectories of some 10,000 fruit flies were examined to determine if the fruit flies were acting in accord with two possibilities. Either completely randomly, they fly in some direction, completely randomly chosen, we don't know, by some mental process, or perhaps completely predictably. That is, do all fruit flies left to their own devices do the same thing? Are they like little mechanistic copies of one another? And the results, rather interestingly, were that they don't act randomly nor predictably. Instead, and rather shockingly, because it's the deepest way that they could act, their behavior was stochastic. So I'm sure most of you are not familiar with the term stochastic. We're actually going to talk about it a little bit more in detail, and you'll see some examples. But in short, stochastic behavior is commonly known as chaos. Okay? That is, the fruit flies exhibit, in some sense, the richest kind of behavior that they possibly could. And they're little fruit flies, nothing more. So we mention this case in part to highlight that experiments are capable of probing that which was originally the domain of philosophers on free will. One might imagine a similar experiment. I'm not going to decide whether this is something reasonable or not. Can't do experiments with people. But one might at least imagine a similar experiment involving people which analyzes our walking paths in a completely uniform room. What are the distinct differences between our actions and those of the fruit fly? Are they notable? Do we act essentially like a fruit fly, or do we act dramatically different? I don't know. I don't know if the experiment was performed, but someone should do it. It's an interesting question. Either way, my point is that we're slowly approaching a quantitative measure of the differences between humans and non-humans that will likely shed some light on a more appropriate definition of free will, hopefully a quantitative definition, and may ultimately provide a resolution to the lesser free will problem. I wish I could continue. There's actually some very interesting experiments in this regard, but I feel it would take us too far afield with regard to time. So we're going to continue by considering another essential definition for tonight. Determinism. It's a term that you'll hear multiple times, so it'll probably be sick of it. So determinism is in the first and most straightforward sense a doctrine that acts of the will, occurrences in nature, or social or psychological phenomena are causally determined by events that precede and natural laws. It's often construed with a belief in predestination, but I'd like not to be so strict. We can't be harsh on it, it's useful. Determinism is, at least naively, a stance against free will. Since determinism, as a philosophical standpoint, grew in modern times out of deterministic theories, it's useful to have a working physics/mathematics definition of determinism, which, like I said, should be more precise. So a physical or a mathematical system of study will be called deterministic if fixing its initial state at any one time determines the state at all other times, both past and future. I purposefully indicate that the state is determined at all other times because all too often, in more relaxed discussions, it's only noted that the state at earlier times determines the state at later times. It's more robust than that. It tells us not only where we're going, but where we came from. For those of us who would like me to define state, perhaps state's less than clear, you can simply imagine a quantity, or perhaps quantities, that specifies all the properties, or if you will, facts, about a system. In the simple case, you've got a single particle, you need to know its position and its velocity at any one time. If you ask about a person, what determines the state of a person, it's a very, very complicated question indeed. Even classically, it's a complicated question, let alone the complications induced from quantum mechanics. Let's further consider mathematical determinism. Imagine a flowing river. Now imagine that at some position upstream, a stick is dropped into the water. We picture the stick following the river's flow. The precise path that's followed by the stick is determined by where and when the stick was dropped into the river. Such is the essence of all deterministic systems. The stick, once caught in the river's flow, has no control over its motion. It merely responds to every push and pull of its environment, the water or rocks, the riverbank, etc. And which particular path is followed is fixed by specifying the initial position of the drop point, and perhaps the time. Sticks dropped in water follow trajectories that are solutions to first-order differential equations. For those of us familiar, it means that you need only specify the initial position and nothing more to determine the full trajectory of the stick. This feature, that deterministic systems are described by differential equations, is generically true. All systems that are deterministic, at least naively, should be described by some underlying differential equation. Now you might wonder how applicable is such a constraint. Certainly it seems to constrain things quite a bit. There's many more phenomena that we can talk about that don't have an underlying differential equation to describe them. So you might ask, how applicable is this? Is this something that is? The answer is very. There are more systems, far more systems described by some underlying deterministic differential equation than anything else. It's very, very successful. I'll emphasize this the success throughout this talk because it's a point that needs to be driven home. How successful this view is. If it weren't successful, I would have no trouble. Most people would have no trouble in throwing it out. But it's its continued success that makes us hold on so snugly. We're going to focus our attention on determinism in the physical sciences, at least for now. Notions of determinism certainly originated very early in human history. That acting in a specific manner or performing a specific set of actions always yields the same end result is fundamentally deterministic. Planting a seed that gives a plant is a type of belief in determinism. That you cook your meat at a certain temperature for a certain amount of time and always end up with the same doneness is determinism. This, in some sense, goes hand in hand with the development of humanity. But at least from our standpoint, Democritus and Leucippus, of Adam fame, both of them, are largely credited with being the originators of determinism. Leucippus claimed, "Nothing occurs at random, but everything for a reason and by necessity." Determinism in the sciences, and thereby in philosophy, comes to the forefront with the Enlightenment. And of particular importance is Newton and his introduction of the laws of motion. Classical mechanics, the physics of Galileo, the physics of Newton, the physics and mathematics of Leibniz, is one of the best, if not the best, examples of a deterministic theory. The alteration of motion is ever proportional to the motive force impressed and is made in the direction of the right line to which that force is impressed. They're beautiful words and they're accurate even today. Mathematically, it reads that the net force is the time rate of change of the momentum, or more commonly, in classroom commonly, F equals ma. Newton's second law provides a second-order differential equation whose solutions are the possible trajectories of the system in question. Once the initial position and initial velocity of a particle or a system are known, the complete trajectory and all future behavior, along with all past behavior of the system, is known and completely fixed. Newton's law allows for both prediction, where will the system be in the future, and postdiction, where was the system before. Both are extremely useful, especially today. As an example, in astronomy, we want to know the future positions of the moons and the planets. We'd like to predict astronomical events. But we would also like to know when past astronomical events occurred, so that we could tie their occurrence to associated historical events. Good examples are the appearance of comets, planetary alignments, etc., where we'd want to know more accurate dates according to a current calendar. Determinism may seem at first glance something foreign to us, but it's not. We experience it in daily life. So here, before I change slide, I hope this is clear. So we consider two particles or two systems in red and blue. The initial position and the initial velocity are specified. They're both some different quantity. And a resulting trajectory follows. We don't know what that trajectory is. It might be very complicated. It's dictated by what forces the system interacts with. So we have to know not only these initial conditions, but also what forces act in the system Fortunately, that's an easier job to determine in some sense. And we end up with some resulting trajectory so that we could use to make these predictions and or post-predictions. So, determinism is not something foreign to us. We experience it all the time. Great examples of this, literally some of the best, come from sports that use a projectile. I know, it sounds silly, but it's true. In all of these cases, the manner in which the ball, or whatever you're throwing, or kicking, or hitting, the manner in which it started, that is how hard you throw it, or kick it, or hit it, or whatever you do with it, and in which direction, determines precisely where it will go. If determinism did not hold up, you could very easily tell your coach that you acted perfectly, but that the ball decided, quote unquote, to follow some different path. Golf would be more boring or more exciting depending on your point of view. Because no matter how much you practice, there would always be some random element. Perhaps you are Tiger Woods and nature is not in your favor. Likewise, physical determinism has been successful in many other arenas, more quantitative arenas, dare I say. These comparatively simple deterministic laws, and I emphasize that, comparatively simple. Nature could have been very complicated, but she's easy in some sense, because determinism is as simple as you could possibly get. These laws have been extremely well verified empirically. From the motions of the heavens to the motions of molecules, Newton's second law has been found remarkably effective. In some sense, we never will throw it out, because even quantum mechanics, as different as it might be underlying this, is nothing more than some theory which in a right regime gives rise to Newton's second law. In that way, Newton really will live on forever. There's some interesting implications for our adherence to Newton's second law. So it indicates that once the forces are specified and the motion of a system is exactly determined by the initial position and initial velocities of all parts of the system. And from this, Laplace, the well-known mathematician, imagined an entity, a thing, a demigod, that could have just such knowledge. Let me quote him, he says it clearer than I will. We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed, if this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes. Laplace suggests here that he believes that determinism is completely applicable to all forms of matter, independent of their makeup, independent of their size, from the microscopic to the macroscopic, from single atoms to single people to all of society. There have been many arguments against the existence of Laplace's demon. Many of such arguments are based on the second law of thermodynamics. In 2008, for example, David Wolpert demonstrated that if two such demons existed, if there were a universe in which there were Laplace demon 1 and Laplace demon 2, and they were interested in each other, they could not predict each other's behavior, according to the second law. That's an interesting result. They would know everything except each other. Whether Laplace's demon could ever exist is not what concerns us here. It's not what we want to call into question. An interesting facet, but a lecture for another day. Instead, we wish to understand if we, like the systems of the classical world, are at all deterministic systems. Are we devoid of free will, as Laplace suggests? As a first objection, and I really mean that as a first objection, there are others, you might claim that free will obviously exists because our actions are simply not predictable. They don't fit this Laplacian ideal. I can't tell you what you'll do, where you were born, etc. There's no way to predict the future given in any sense the present data, like Laplace promises. I can't predict who in this room will sneeze. I can't predict if anyone will jump up and scream like a monkey. But I wish to emphasize, predictability is distinct from determinism. Some systems are completely deterministic. That is, their future state is exactly determined by their past state. All of their previous states completely specified by giving conditions at just one time and one time alone. Yet, their behavior is completely unpredictable. I pulled up a YouTube video of a mathematical model of the so-called double pendulum. It's a system composed of two bobs. They're often, and in this case, composed of pendulum bobs of the same mass. They're attached by rigid rods. The rods could be of different length. In this case, the simplest, they're of the same length. And such a system is deterministic. It's described by Newton's second law. This is obviously, it's not empirical. This is a mathematical model. It was done on Mathematica. It uses Newton's second law. It uses well-known weight is mg for those of us familiar from physics class. It is, however, accurate in the sense that you can look for special modes from the solution to Newton's second law. You can find those special modes in the lab, etc. And most interestingly, it's a chaotic system. As simple as it is, it's a chaotic system. Let's take a look at it. So they were all started in exactly the same initial position. I'll play it a second time if you'd like. And you can see, here we are just a few seconds later. Their motions look completely uncorrelated. Could you ever tell, here we are, 10 seconds in, that the motion of these bobs was exactly the same to begin with? The initial conditions very nearly the same, to within hundredths of a degree difference. There'd be little to no way of knowing it. That is, the correlations are completely masked, even a very short time later. The motions look random. I emphasize look because they're not random. If we had a computer better designed, if we had more mathematical capabilities, we would be able to make more accurate predictions for longer periods of time. The correlations would not so quickly become hidden. But as it stands, we have finite computing power, and with finite computing power, you end up saying that the motion looks random. Indeed, it's a good approximation to say that it's random after a certain chaotic timescale. The point being that these are deterministic systems that look completely random. That is, the motion cannot be predicted. So the question, then, are we such systems? And with Bjorn Brem's experiments, it suggests that the fruit fly is such a system. It's perhaps even more natural to say that we are likely such a system. Here is a very incomplete list of deterministic systems that exhibit chaos. Firstly, we have the double pendulum. How do we know? We just saw it. In addition to 3 or more bodies interacting gravitationally or electromagnetically, or absolutely worse, both are chaotic. There's actually something interesting here because our solar system is composed of 3 or more gravitationally interacting bodies. And for long periods of time, we could make predictions, but we can't make predictions forever. We don't know how stable our lovely position in the world quite is. And that's really, it's interesting. It's interesting for us because we want to know where we're going. And because of chaos, we actually can't. Not exactly. The weather, at least part of the reason that we're here tonight, as opposed to 2 weeks ago, is because the weather is a chaotic system. We've all seen how poorly our weathermen predict the future, even by a few days. And I think that we should all leave this evening saying, wow, that is a tough job. They have coupled nonlinear partial differential equations to solve. The modeling is very, very difficult. Making predictions even on short time scales is amazingly difficult. And they do a pretty fair job given what they've got. Fruit flies, they're chaotic systems. Should we be on that list? Possibly. The purpose of this look at chaos is to convince you that just because there's great difficulty in predicting what I'll do next, the future behavior of a particular system does not guarantee at all that it's not deep down, not fundamentally a deterministic system. It is at least a possibility that we cannot ignore. And this argument, which is often presented by those adhering to free will, I won't name any names, you know who you are, is really, upon closer examination, not that convincing. We really do need more, especially if you fall in the camp of a believer in free will. So now that I've convinced you, hopefully, at least in part, that there's a prominence of determinism in the laws of physics, let's consider our hierarchy in that list. We are undoubtedly composed of molecules, and those molecules are undoubtedly composed of atoms, and those atoms are undoubtedly composed of subatomic particles. Does everyone agree? If not, talk with me afterward. If determinism is demonstrated for the simplest ingredients, then determinism is induced at all levels. Who's convinced by this? One might object to this strict reductionism, as it were. But it's worked so beautifully before. By describing subatomic particles in full, we can describe atoms. And by describing atoms in full, we can fully describe molecules. Shouldn't this continue until we are reached? Where in this chain would we find a break? What's the weak link? It seems solid to me. Talking for literally a single moment, as I've done with a physical chemist here and there, will reveal very quickly another objection. Yes, sure, we can describe molecules in terms of atoms, but it's so hard. In principle, it's possible to reduce complicated systems to interactions among more basic components. But in practice, it can be, and often is, virtually impossible. Biologists don't study elephants by asking about how hydrogen can bond with oxygen to form water. Carpenters do not learn how to build houses by first learning how to smelt steel and melt it to form hammerheads. The key phrase here is in principle. We're concerned with what happens in principle. And yes, in principle, we are physical systems. We're composed of interacting atoms, so that an argument for induced determinism does seem to hold, lest someone can spot the knot or indicate a weak link. I really don't see one. If we are made of atoms, then a scientist studying atoms is actually a group of atoms studying themselves. Just a little food for thought. We can now make a sharp statement of the free will problem, as I've alluded to in my title. If the laws of nature are deterministic, and we are elements, quote unquote, of nature, i.e., the laws apply to us, then we are deterministic and therefore have no free will. It's clear that there are at least two key assumptions that enter into this conclusion. We had to assume that the laws of nature are deterministic, and we had to assume that the laws of nature apply to us. Let's proceed by examining their robustness. For nearly 100 years, it has been known that the formalism of classical mechanics is not sufficient in describing the physical phenomena that we observe on an atomic scale. Thus, nearly 100 years ago, the mid-1920s, was born quantum mechanics. When I was describing the success of classical mechanics, many of you here probably wanted to scream at me, maybe punch me. Classical mechanics failed, and quantum mechanics is here to the rescue. Obviously, in thinking these thoughts, you are absolutely correct. Classical mechanics has proved absolutely insufficient in many, many ways. I won't list them here. And quantum mechanics has very elegantly patched all of its holes. I really mean that, all of its holes. I couldn't think of one case where it didn't patch a lovely hole in classical mechanics. Can it also help us bypass the free will problem? This would be a remarkable thing if quantum mechanics patched all of the holes of classical mechanics and helped us settle the free will debate. In short, it might help. Most of us understand quantum mechanics as a theory which has intrinsic indeterminacy. The Heisenberg uncertainty principle comes to mind. The textbook interpretation of quantum mechanics, however, that we all learned, is not correct. The correct interpretation of quantum mechanics is an area of active research. I stand here as an example. Namely, quantum mechanics, as we understood it, as we all understand it from the textbook case, where a measurement is made, a wave function collapses, and from it we determine probabilities, is a very, very wrong thing. Wrong on a very deep level, because it forces us to introduce a process, measurement, that cannot be probed any further. And although, from a practical standpoint, the predictions are rock solid, in every experiment ever done, the resulting predictions are exactly correct, literally to many, many hundreds of decimal places, the underlying interpretation is not right. It can't be that there is some process as big or as needed as measurement that cannot be analyzed. We build measuring devices. Those measuring devices are made of parts, they're made of nuts, they're made of bolts, they're made of lasers or whatever sort of system you deal with, and we should be able to understand those processes from a fundamental quantum mechanics standpoint. Now, it's a big thing to attempt to do this. It's not something that will likely come to fruition in the very near future. But once again, I emphasize in principle. In principle, we should be able to accomplish this. There's two examples of interpretation of quantum mechanics which attempt to bypass these issues. They attempt to resolve them by introducing perhaps some weird things. I'll mention them in passing. So one is the many worlds interpretation, or the many minds interpretation, which posits that an act of measurement is nothing more than a physical interaction, which is good, but unfortunately has to say that we are one of an infinite many worlds, quantum worlds in a quantum superposition, and there's Bohmian mechanics. So Bohmian mechanics is at first glance, a little nicer. It tells us that particles may follow a trajectory, which is an appealing feature, but it itself is often disregarded because of the fact that it has two guiding laws. Unlike having F equals ma from Newton's second law, it has both a Schrodinger equation and then an additional Bohmian wave guidance equation. So it's unappealing in that sense. I mentioned both of these interpretations, really three, because they are fully, absolutely deterministic interpretations of quantum mechanics. So many of us would understand quantum mechanics as introducing some sort of randomness, but that's not necessarily the case. Bohmian mechanics describes atoms perfectly well, makes the same predictions that quantum mechanics with the standard interpretation makes, and yet it's completely and entirely deterministic. Likewise for the many worlds or the many minds interpretation, without perhaps the complication of many quantum superpositions of worlds. There's another reason why quantum mechanics doesn't help. Perhaps you adhere to the view that quantum mechanics is indeterministic, and it will turn out in the future to be truly indeterministic. It's not going to help the cause of free will. Quantum phenomena exhibit randomness. Consider a great example, that of a sample of radioactive material. In any given time interval, there's some probability for an atom to undergo a random decay process. The process appears completely random. We've tried to understand if there's something more deep going on. We can't say anything. It seems random. There's no known variable that might allow for the prediction of which atom at any given time will decay. We call them hidden variables. Is it possible that our minds are exactly this? Quantum systems, and their decisions really are, fundamentally, quantum events. It's possible. I'll give you that. It's possible. But then our decisions, if dictated by quantum randomness, should at best be random, or exhibit some sort of randomness. Randomness is not free will. Our decisions don't, at least apparently, look random. Instead, they're often logical or orderly. If I said, "Why did you decide X?" you might provide a list of reasons as to why you decided X. Even the lowly fruit fly doesn't exhibit purely random decisions. We know that. That's an empirical fact. And so to say that quantum mechanics will provide any more insight into the problem of free will is at best stretching what we've got. It may in the future. There's always the possibility, but at least now it seems unlikely. We see that our original assumption 1 is overly restrictive. The laws of nature need not be deterministic. They may, in fact, exhibit some amount of randomness. Either way, the standard notion, the Cartesian notion, the notion of Augustine, of free will, is at best highly suspect. And for those of us rooting for free will, this is not a good turn of events. We wanted to weaken these assumptions, not strengthen them. Perhaps it may be that assumption 2 has the greater weakness. It might save us. Naively, it would seem that the laws of physics do actually apply to us. We are attracted to the Earth gravitationally, just like all other objects. When we trip, like my stick fellow here, we fall. We're certainly made of the same substances. We have every other reason to believe that they act the same inside us as elsewhere. That hydrogen bonds to oxygen to form water, seems to act the same way as it does in our body, as it does in the ocean, as it does as a vapor in the atmosphere. Philosophically, it would be a very weird and perhaps cruel dualism if the laws of physics applied everywhere but with us. Our goal, at least in part, in attempting to understand the laws of physics is to understand ourselves, and it would be perhaps humorous, if they applied to everything we studied, but really fell short for you and me. It seems absurd to stand up here and say that the laws of physics might not apply to us, but this viewpoint is not at all new to physics. Newton, indeed many other physicists of the Enlightenment, did not at all recognize a free will problem as we do today. This is because they simply did not believe that the laws of physics applied to us directly. Yes, they understood that we were made of the same substances, and yes, if we tripped, we would fall to the ground like any other object, but we were endowed with an ability to act outside of the determinism that guided, indeed binds, the rest of the universe. We had something that imparted to our physical bodies a sort of exemption, a get-out-of-jail-free card. More recent manifestations of this view arise in questioning interpretations of quantum mechanics. In particular, the well-known physicist and mathematician Eugene Wigner proposed that it was consciousness that acted to collapse the wave function. Needless to say, it's a far less common view to encounter today. It's weird, period. The question of whether the laws of physics applies to us is, once again, a question of the validity of reductionism. Clearly, one cannot argue for reductionism alone. Instead, it's something that should be tested against experiment. There should be empirical evidence for reductionism or empirical evidence against reductionism. Either way, philosophical argument is not what we need here. Suppose that one wishes to describe a molecule. I know many of us here do, actually. One's first recourse, a very natural one at that, is to consider the molecule as composed of atoms. One supposes that the atoms exist and that they interact in certain ways. That is, one constructs a model of atomic behavior. Then the model is used to make predictions about the molecule, which is compared to experiment. In so much as this process is successful, reductionism holds up. Perhaps a brave soul might stand up and claim that reductionism is going to fail at some level. We're going to see it. But they are standing up against a mountain of evidence in support of reductionism that is 1,000 years old. I have here, before I change the slide, an image of a duck, but from a Descartes automaton point of view. That is, if one believes in true reductionism, then all of us animals are composed of individual interacting parts, which if we understand completely and entirely, we understand the animal completely and entirely. It's meant here mostly for amusement. We know ducks are much more complicated than that. So we have, up until this point, been looking at determinism from a physics standpoint. That is, we've been looking at human behavior, the presence of determinism in human behavior, as induced from microscopic constituents. This is a bottom-up approach to determinism. It could be that such a bottom-up approach is correct, but that it's very well hidden in our macroscopic world by the presence of chaos. That's a logical possibility. But there's even more support for determinism from a top-down approach. That is, determinism makes an appearance, rather remarkably, in psychology, in neurobiology, in neuroscience, etc. And that's a pretty remarkable feature. Not only can we argue for its success from the bottom up, but also, at least in part, to variable success, from bottom down. Various approaches in psychology take the standpoint that humans are deterministic and have absolutely no free will. Behaviorism is the prime example. One may take the source of the determinism as being outside the individual. That is, we are merely responders to various external stimuli. More specifically, the behaviorism championed by B.F. Skinner, the well-known Harvard psychology professor, posits that human behavior is essentially dictated by chains of reinforcement and punishment that give us the impression that we are free to choose. Our behavior is modified by our own particular history of reinforcement and punishment, which forms the basis of which we now know as operant conditioning. Most of us are probably familiar with classical conditioning. That might still well apply. Classical conditioning is in Pavlov's dogs. We've all heard of Pavlov's dogs. It's possible that our behavior is dictated by both, okay? But the point is that emphasizing that we are merely responders to external stimuli does a good job of describing the way that we behave without forcing us to consider any notion of free will. It's similar in some distinct sense to the atom describing the molecule. We can be in large part described as just a responder to some external event. We're similar, psychologically speaking, to the stick in the river. A mild example of this is the study by Bandura and others since then. Bandura was working in the mid to late 60s, looking at children. Namely, children with violent parents are in fact statistically more likely to in turn become violent parents. And this is, in some sense, an example of operant conditioning. Children were exposed to this behavior, and their freedom to either avoid such behavior or to partake in such behavior was at best influenced. The examination of brain activity is a relatively new tool in the search for the free will. Current techniques include the well-known electroencephalograph, an EEG, which measures electrical activity or potential differences across large portions of the brain, and the less well-known, slightly newer, magnetoencephalograph, an MEG, which measures magnetic activity. Even PET scans or MRIs can measure blood flow differences. They can also be coupled with tracers. All techniques to probe what's going on in the brain when various thoughts or decision making is taking place. There's a thought-provoking result coming from this field, not fairly recently actually, in the past few years. So brain activity underlying a given decision occurs before a person consciously apprehends the decision. In other words, thought patterns leading to conscious awareness of what we're going to do are already in motion long before we know we'll do it. That is, they've done a series of experiments where people have been asked to perform some act of free will. For example, the twitch of a finger or the flick of a wrist or to push a button. And they look at brain activity as a continuous function of time while they perform these acts. And we can see distinct changes in the brain that predate roughly 5 seconds, between half a second and 5 seconds, depending on the study, that predate the action. Okay? So that's kind of interesting. In addition to, we have these people cite when they felt that they had made the decision, that we had made a decision to push the button or flick our wrist. And in all of these studies, although the time interval varied, in all of these studies, the result was that there were changes in the brain before they felt that they had made the conscious decision to do some act of free will. Without conscious knowledge of why we're choosing what we're choosing, it seems apparent that we cannot be using at least a classical notion of free will. That is, it seems that the decision-making process is at best much richer than we would originally think. When we say, I've made a decision, for example, where to go to school, we imagine that we lay out a list of things. I've considered this, I've considered this, I've considered this. They enter into my decision-making faculties, I'm a conscious being, I'm making these choices based on logic, etc. But these results seem to imply otherwise. Namely, they seem to suggest that our decision is not being made at all by the conscious portion of our brain, which is at least an interesting result. If not, it's saying something even bolder, namely that our free will, at least as we would understand free will, is really, really in question here. Such conclusions should be taken with a grain of salt. Namely, the research does seem to indicate rather boldly that the decision being made by the individual, at least, is being made by his or her brain. And that's an important thing to mention. So, although it shows that it's not the conscious portion of the brain that's making the decision, it is at least the brain. And so that would at least say something about the behaviorism approach. Namely, it's not strictly external features that are doing the deciding. Instead, it's the product of external features and how they impacted the unconscious brain that does the deciding. So in that sense, it's a +1 for free will. It could have been worse, in other words, where the decision-making center was decided to be outside the individual. More interestingly, the possibility of neuroprediction is on the horizon. That is, studying brain activity patterns may allow the prediction of what decision will be made before an individual has consciously made a decision. And this is especially interesting. Imagine that you're undergoing some sort of brain scan, and I ask you a question, some decision that you have to make. And I notice a particular pattern on the brain scan and know from that what decision you'll make. I then stop doing the brain scan and I send you on your way, and you have not made your decision yet. You come back the next day, and I ask you, what decision did you make? And every time I successfully predict what you've decided. You thought that in going home you considered the facts and made a wise decision, when really your decision was made yesterday, and I knew it already. Now, it's not here yet, but it's getting ever closer, and at least for short time intervals, I extrapolate by saying perhaps a day, but at least for shorter time intervals, it seems that this might be a realistic possibility. And it once again really does lead to either a very dramatic reinterpretation of what free will means, or it means the abandonment of free will from this standpoint. We've assumed up until this point that determinism implied that we do not have free will. And in the strictest sense, in the very strictest sense, it does. The term free will, as it does imply, determinism completely removes that. Dramatic change. However, the lesser of free will problem, that we still need a good definition for free will, something that applies to us instead of animals, etc., allows some freedom here, and of course philosophers who are bright people took some liberty with this freedom in definition. So we're going to consider the philosophical stance of compatibilism, which defends, rather remarkably, the point of view that determinism itself does not eliminate the possibility of free will. Define free will to be the state in which a person acts without external influence. That is, a person acts with free will if they act without any coercion. Then one can say that their will is free, independent of whether or not it is determined by deterministic laws. Compatibilism does this by weakening the notion of free will to that of uncoerced will. That is, it really is based on a bit of tautology. We have to really kill what we would have originally deemed to be free will, as in making free choice, to something that allows us to make a choice without known external factors. I don't know if I completely buy this myself. Frankly, I don't like word games, and so this, in my book, falls under a bit of a word game. But with that said, there have been many, many well-known philosophers and theologians that have defended this view very, very staunchly. St. Thomas Aquinas is one of them. Okay? It's certainly worthy of mention for that reason and for that reason alone. In some sense, when we use the term free will in court, this is actually all that we need. Was that person coerced? Do you freely marry this person? Right? Yes, I do. I'm not being coerced by someone. So this is, in some sense, a useful thing to have in mind for more practical matters, but I think that it really does bypass the more fundamental problem. It really is just a way of skipping over the nitty-gritty / interesting details. What if we have free will? What if? Rather remarkably, if we're actually free, that is, determinism really does not apply to us. All that I've said, a bunch of BS. It does apply to the rest of the universe. Determinism really does apply to the rest of the universe, but not to us. Or likewise, if randomness works for the rest of the universe, perhaps quantum mechanics is truly indeterministic, but not for us, then we have at least the hope of discovering it empirically. Just as the Bjorn Brehm experiment is currently working with fruit flies to indicate chaotic behavior, we may one day hope to extend this notion to people. And the fruit flies, which exhibit chaotic behavior, is fundamentally deterministic, and such we'd expect. Similar experiments with people could reveal truly indeterministic behavior. That is, we proceed with the experiment with people and we find that there is a distinct difference between the decision-making process of people and the decision-making process for animals, or fruit flies, for whatever thing you might be investigating. To quote Christoph Koch, there's no way the conscious mind, the refuge of the soul, could influence the brain without leaving telltale signs. Physics does not permit such ghostly interactions. That is, we may empirically uncover our own free will, and this is a truly exciting possibility. For those of us that liken free will to that of a soul, for obvious reasons, it would literally mean discovering through science some notion of soul. In a world where we're constantly told that we share greater than 90% of our DNA with our nearest primate relatives, it would mean discovering that we are truly special. If we have free will, then there are two distinct logical possibilities. In the first possibility, we might be found unique. That's the exciting one. People, and people alone, are equipped with free will. We're distinct from animals. Indeterminism is part of our very nature. That's the excitement. The second possibility, it might be that the freedom is not, in some sense, bottled up in people and people alone. That is, we have to give up some of our specialness. And the freedom trickles down to lower entities on the complexity scale. Two well-known physicists, John Conway and Simon Kochen, have considered this very possibility. It's explored in a 2006 paper in Foundations of Physics, the title of which is The Free Will Theorem. If you'd like to read it in full, it's available on the archive, so that's a possibility if you're interested. I'll give you a course look right now. So the theorem states the following. They make three assumptions, which they actually refer to as fin, spin, and twin. I think mostly to be amusing, but also quirky. They are physicists after all. They're as follows. So number one, there's a maximum speed of propagation of information. Not necessarily the speed of light. They don't make the assumption in the paper that it's the speed of light. More than likely, it would be the speed of light. We don't observe any other fundamental limits, so it would seem that only the speed of light is the natural thing to say. Two, the squared spin component of certain elementary particles of spin 1, namely massive elementary particles of spin 1, taken in three orthogonal directions, are permutations of 1, 1, and 0. So this is sort of a technical requirement. I'm not going to go into details, obviously, We can talk about it perhaps in the question and answer section or afterward. And number 3, it's possible to entangle 2 elementary particles and separate them by a significant distance, so that they have the same squared spin results if measured in parallel directions. So this, we know, is a very feasible thing. Experiments have been done in this regard that were separated by many, many miles and on very, very short time scales. In fact, all 3 of these assumptions are very, very feasible. I mean, we see no reason to not trust any of them, right? In fact, if any one of them were found lacking or failing in some way, it would mean a pretty dramatic change in our notion of fundamental physics. So, assumptions. And now to the setup. So the experimental setup for the free will theorem, it's a theory paper, but they're discussing well-known experimental setups that look something like this. It's that of the EPR, or Einstein-Podolsky-Rosen experiment. So spin 1 particles, a photon is a spin 1 particle, but it's not massive. That wouldn't apply. You need a massive spin 1 particle like a nucleon. They're prepared in some particular states, and they're allowed to travel to distant laboratories where the spins are measured. More properly, the squared spin components are measured via Stern-Gerlach devices. For those of you familiar, congratulations. For those of you not, ask me or live on. It was essentially this experiment that gave Einstein, Podolsky, and Rosen great difficulties in trusting quantum mechanics. They had other reasons, but these experiments in particular are really nasty because they imply a very odd type of action at a distance. You get correlations between the results measured in each of the distant labs that seem to propagate many, many times faster than the speed of light. In fact, very recent empirical results imply that the speed of correlation is some 20,000 times faster than the speed of light. And that's a minimum value. It might very well be infinite. Seems possible. Quantum mechanics will say it is. So most importantly, given these assumptions, what can we conclude? Well, rather remarkably, if the 2 experimenters in question are free to make choices about what measurements they make, then the results of the measurements cannot be determined by anything previous to the experiments. That is, there's a clear failure of determinism here. That is, what the experimenter decides really fixes the results of the experiment in some sense that nothing beforehand could have ever deduced or known. There can be no such thing as a Laplace demon in this world. It is not, in my opinion, quite correct to call this a free will theorem. It's really a theorem concerning indeterminism. And it could be called, quite correctly, an indeterminism theorem. I'm also skeptical of the claims that the authors that the theorem was interpreted in a variety of quantum mechanics interpretations. In reading this paper, I see the well-known hallmark of orthodox quantum mechanics interpretations, which has the innate indeterminacy, the problem of measurement. And I see no attempts to make an interpretation either in many worlds or many minds or in Bohmian mechanics, and I wonder if one attempts a reinterpretation of the result, if you might basically end up, in some sense, weakening the overall theorem, that there is something which determines the end result, but that it's hidden, for example, so that their theorem really doesn't hold infinite water. There's good reason to think this is true, because it's been very, very well known for a long time that at least Bohmian mechanics does reproduce everything that quantum mechanics has, and so there would be nothing standing in the way of it reproducing the results of the free will theorem. Okay. At best, however, it does allow us to make some statements about how determinism or indeterminism propagates between hierarchy. Namely, it does seem to suggest that if you've got indeterminism at any level, then there'll be indeterminism at all levels. Or likewise, if you have determinism at a fundamental level, you have it, once again, at all levels. Free will or feeble illusion. Thanks, guys.
Thank you, Elliot. Now, we will have time for questions, and it seems that the snow hasn't come yet, so we're safe. All right, so if you have a question, Patrick and I will bring you microphones. Okay, you can stay on that side then.
Why does it look like, and maybe more importantly, feel like we have free will?
Yeah, that's a really great question. So it depends on your standpoint. B.F. Skinner would likely say that it feels like we have free will because we're not consciously aware of the external influences. Okay, so for example, when you toss a die, it appears random. We know that it's really not random, but it just depended on things that are not very easily accessible to us, like how our hand twitched when we released the die. So in some sense, we take a shortcut. We take a mental shortcut and say, I made that decision just because I don't know / I can't analyze mentally all the things that coerced me or forced me into making that particular decision. From a deeper standpoint, we could say that we blind ourselves. That's always a possibility. One might argue, evolutionarily speaking, that there's some advantage, there's some evolutionary advantage in believing that you have some freedom. One might also argue that we, as part of the system, are well, I was going to say that since we're part of the system, we have finite information about the system, right? It's a lot like it's a lot like asking. It's like asking great things of something stuck in a box. Okay, so it has a very limited point of view, and that if it were to make assumptions that it has freedom to move around its box, then it's happier. Period. There's I think there's a variety of ways to go answer that. I don't know. In short, I really don't know. I mean, it certainly feels as though we're free. I agree with that. It feels as though we're free. Where are we?
I understand your depiction there of reductionism, where physics underlies chemistry, and chemistry underlies biology, and biology underlies neuroscience, and neuroscience underlies psychology, and so on.
Right.
I happen to think there might be a transition or a discontinuity in there, in that somehow energy, living matter evolved consciousness at least one species, ours.
Mm-hmm.
And I know you had a quote, the Christoph quote, the Caltech gentleman, about that they trace nothing in physics
Yes.
from the mind to the body, but there seems like a lot of mind-body interaction, placebo effect, and so forth. So
Absolutely.
how would you comment on that, please?
Yeah, so I think I'm glad. First of all, thank you for raising this issue. I was hoping that someone would take this view. Namely, I'm rooting for you, okay? I hope that there is, exactly as you put it, a sort of discontinuity. There's some break. That is, there really is a failure of reductionism at some level, okay? I sincerely hope that. But the possibility at least exists that there isn't such a break, okay? Now, obviously, I mean, people are very, very complicated things, okay? Period. And so it's going to be tough to do some experiments and peel away as much as we can to reveal what we are on the inside. But for fruit flies, it's decidedly an easier thing to do. And so you can examine their behavior, maybe in the upcoming years examine something more complicated than a fruit fly, and so on. And we'll get some picture, a better picture at least, of what their decision-making system is, okay? Is it possible that there's going to be some clear break, like chimpanzees or people or something are very distinct? Absolutely. But we have to, at least at this point, concede that there's a possibility that there is no break. Okay? And that's really my only argument. Okay? It really comes down to we don't know yet.
Hi. Taking the reductionist view we've just been listening to, in physics, there's no such thing as the sum of the parts or a whole. They're discrete particles. Whether it's a subatomic particle, whether we want to aggregate it an atom, they operate independently, though they influence each other. And they consist only of objective states, like a spin of electron. Is that correct?
No, I wouldn't say they only exist in objective states.
Well, give me an example of a subjective one, because where I'm going with this is very simply is we see each other right now as a whole.
Right.
And there's no objective called the color. The color is a subjective thing, and we
Sure.
perceive the whole room. So which subatomic particle, which atom, or which molecule is the cognitive unit that's possessing all of this information right now while we're looking at each other? Because I'll tell you, Christoph Koch, 20 or 30 years looking for it in vision, it's gotten very, very, not got far at all.
So, okay, let me break that up into some pieces. So I would say, firstly, that there's the possibility of subjective states. There's a lot of people that would like to interpret the wave function epistemologically, okay? They haven't been exceptionally successful, okay? So it's more likely that the wave function, the quantum mechanics will be led down an objective road as opposed to a subjective road, that it's not making statements about what we know or what we can know, but what's real, which is good for a scientist because that feels right. It feels like we're studying something out there as opposed to studying something in here. But at least the possibility of there being non-definite states clearly exists, depending on what you define as an objective state, right? So quantum superposition is a prime example of that, right? So classically, there is a particle, it follows some trajectory, it moves along some path, it has some velocity every time. Quantum mechanically, we know that's not true. A good mental picture is that of a many-fingered approach. There's many, there's many paths, or there's many possibilities, and then some process selects one of those possibilities. So I would say that, that naively at least would fit your description as a state that's not objective, right? Like for example, Schrodinger's equation says that we're allowed to talk about alive dead cats, right? Classically speaking, the cat is either alive or it's dead, and yet we're forced, because of its empirical success, to admit the possibility of a live dead cat. I'm not saying that would actually exist macroscopically, but still the point is made. And then what cognitive ability determines the... What was that?
What's doing the perceiving?
I would say that perception is really nothing more than a sort of a cross correlation. So we do experiments where we determine correlations between quantities, right? And so then in part, the notion of perception is that I form in my mind the idea that blah, 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 whatever it might be. And so then we would say that's a type of correlation forming with the atoms or molecules that form in your brain with something external to it, right? Meaning, for example, somebody asks a question, right? And then you generate an answer, okay? That process, I would say, is a correlation between information in your brain. So there's some information that leaves some atom or molecule or neuron or whatever it is in your mind, and it's transferred to someone else's. It changes the state of some neuron, perhaps going down as tiny as some molecule. Does that make sense? Is that reasonable?
That's a partial. I'll grant easily that it can change the state of atoms. Okay, so there's
Okay,
something
good.
that happens, you get the process. Now you have an end result and a new arrangement of atoms. Someone
Yep.
still has to take that arrangement of atoms and create a perceptual experience.
I would say that's.
Unless you don't hear me, I think you do.
Well, yes, I hear you.
I see you too.
Right. I agree. I see you, but in some sense, we're trying to cut away any excess baggage, and in the simplest
Close my
possible.
eyes.
Well, you could. That's a possibility.
That's right, thanks.
I mean, I sort of see your point, but I mean, I think it's pretty clear that I mean, at least in the crudest sense, perception as correlation is pretty valid. You know, it gets maybe 90% of the picture right. You see my point? Meaning, maybe we're missing something, okay? Like I said, I'd like to say that we're missing something, but that we have a good chunk of it is no small beans.
So I think the two of you have different theories, reductionism versus emergence.
I wouldn't call it emergency.
What would you call it?
Emergency.
Call it the immaterial mind over soul.
Okay, all right, that's true too. But I do think there is something to be said for the emergent kind of reality. Do you want to ask something,
Yeah, this is way over my head. However, it seems to me that the fellow from Caltech indicated that there cannot be anything spooky, ghost-like, as he indicated.
Yep.
But that doesn't seem to me, that doesn't necessarily preclude the existence of an external agent, i.e. spirit, i.e. mind, leaving a physical trace on something. Once there is an interface, there's a paper trail, so to speak. But that doesn't necessarily mean that everything has happened internal. There could be an external agent causing that, no?
I think you're exactly right. I think you're saying the same thing, actually. I really mean that. I mean, what he's saying, at least naively, is that if there is something else, something external, then it will leave a paper trail, exactly as you put it. That you can't hide it, in other words.
I'm sorry?
You can't hide it. Meaning, if there were something external, if there were something spiritual, if there were a soul, if there were, however you want to interpret it, if there were something, then it would leave an impact in the physical world that at least at some point we could possibly observe. Does that make sense?
Yes.
You're in agreement with him, in other words.
Yeah, essentially, yes.
Yeah.
Although the language, yeah, I think so, yes.
However you want to phrase it, you use the term paper trail. He's saying there can't be ghostly interaction, meaning there can't be interactions which are, in some sense, blind to our experiments.
Okay, I think maybe one more question if anyone is ready for it, and we'll wrap this up so you can get home before the snow.
A quick comment, then my question.
Sure.
The 5 seconds before the conscious decision,
Yep.
brain
Yeah.
change.
Ask a question.
Could
decision
that
making.
be considered the paper trail from the immaterial to the behavior that was just being discussed?
The time delay itself? I don't know. That's a good question. What does the time delay mean?
Meaning that
yeah.
there's something that can't be directly perceived, the mind or soul or whatever. Then there's something that can be perceived, and then there's the actual behavior or decision. But
Yeah.
what I really wanted to ask is, you're someone who's thought about this a lot, and you must have talked to many people about this, right?
Sure, absolutely. As many as I could.
With very strongly held opinions on either
Yes.
side.
Definitely.
This has no objective value in deciding anything, but I'm so curious. Have you noticed any differences in the pro and con people in how they behave, how they think, how their morality, their interactions with others?
Yeah, that's a great question. And you know what? Rather remarkably, no, I really haven't seen any difference. That is a really great question, because I think
evidence for or against?
Yeah, I mean, it really harkens to something very, very universal, right? That independent of our stance on this, there is something guiding our behavior. I'm not sure if it's purely cultural, that very well might be, but there is something independent of what opinion we formed on these things that determines, at least roughly, how we're going to behave when we interact with each other. but more deeply, I mean, I don't know any of these people on such a very deep personal level. I wonder very often how, what the interaction is like between spouses where one is an atheist, or between friends where one, really does not believe in free will. And that I'm not privy to, unfortunately, I guess. Maybe, fortunately, I'm not sure. It's a possibility.
That's our next question. So I want to thank Dr. Tammaro. I'm sure we learned a lot this evening. And I hope you'll be back again soon. We have 2 lectures coming up, March and April. Be sure you're on our mailing list so that you have the dates straight. We also have an open dome night coming up in April. What is it? April? I forget. 8th. The April 8th. We're hoping that would be over at our main campus. So be safe going home, and luckily we've missed the snow. I hope you all get home before anything starts. All right, thank you.